we are going to be talking about Wien's displacement law. The law says that the black body radiation curve will peak at different wavelengths that are inversely proportional to its temperature. Now, in practice, if I had a black body which absorbs perfectly all of the EM radiation, but also if we heat that body up, it will start emitting. Now, if we raise the temperature to different amounts, the peak wavelength will be different. The higher the temperature, the lower the wavelength. For instance, if I had a pretty high temperature, about 5,500 Kelvin, you're going to see that my peak wavelength is down here. It's quite short. However, if I had this green curve over here at a lower temperature, let's say 4,500, then my peak wavelength is a little bit longer. And if I had this sort of red curve at 3,500 Kelvin, you're going to see that my peak wavelength is now even longer. Mathematically, we can write this statement as lambda max, the peak wavelength, is inversely proportional to the temperature. So additionally, we can also write this down as lambda max times the temperature is equal to a constant. Now, this constant normally has a value 2.9 times 10 to the power of -3. However, we are not normally given this in the exam, so if one quantity times another quantity is equal to a constant, one way that we can use to tackle questions is that we can just rewrite the above formula as lambda max 1 times T1 is equal to lambda max 2 times T2. Now let's apply Wien's law to a problem. We have that the peak wavelength of a star is 580 nanometers when its surface temperature is 6,000 Kelvin. Now, a different star has a peak wavelength of 520 nanometers. Find its surface temperature. Okay, well, let's tackle this one. The first thing to do would be just write down Wien's law, and that is that lambda max of my peak wavelength times the temperature is equal to a constant, and what we can write down is that lambda max 1 times T1, that will be for the first star, it will be equal to lambda max 2 times T2, which will be for the second star. Now the peak wavelength of the first star is 580 nanometers. Its temperature is 6,000 kelvins, and this will be equal to the second peak wavelength, which we're given here to be 520 nanometers, times the temperature that we're looking for, T2. Notice that I've not included the nanometers on either side of the equation, because otherwise they will just cancel out immediately. So all I need to do really is just rearrange for T2, which is going to be equal to 580 times 6,000 divided by 520, and if I put this into a calculator, I'm going to get 6692 Kelvin, which up to two significant figures will be approximately equal to 6.7 times 10 to the power of 3 Kelvin. Okay folks, so hopefully Wien's law makes sense. If there are any questions, please feel free to drop a comment down below. Thank you very much for watching, and I hope this video was useful.